Welcome. So the topic we'll be discussing in today's session is Mutex locks and semaphores. So these are also some of the methods to achieve process synchronization. So in the previous class, we have discussed about hardware-based process synchronization, but these hardware-based synchronizations are quite complicated, and also generally it is inaccessible to programmers. So generally, there will be software based solutions which will be used by the programmers. So, Mutex Lock is one such software based solution to solve the critical section problem. So, the idea is simple here. First, before accessing the critical section, the particular process should acquire the lock. It should get the lock and then it should access the critical section, and after accessing the critical section it should release the lock. So this is the whole concept on which it works, and calls to acquire and release must be atomic. Is when any process is executing acquire lock acquire function, then that at that time the process cannot be context switched. Similarly, if some process is executing release, so release also will be an atomic instruction, that is, it cannot be context switched. There is a problem with mutex lock. The problem is it may require busy waiting. That is, if somebody is already in the critical section, if some process is already in the critical section, then the other process should keep on wait in a while loop, and it should keep on check whether the lock is available or not. Previously also we have discussed some examples like that. So this is called as busy waiting, or this problem is called as spin lock. So this is a problem because at this time the CPU is not doing any useful task. It is just waiting, and it is checking whether a lock is available or not. Okay. So in many algorithms related to process synchronization we have seen this happens. That is, if one process is in the critical section, then the other process will be keep on waiting through an infinite loop until that particular lock is available. So that is called as busy waiting or spin lock. So basically that is one of the drawback. So in mutex lock also that problem is there. So this is how normally the code for mutex lock appears. So there will be two functions, acquire and release. So before entering the critical section, the particular process should execute acquire. So in acquire, what it does is it checks while not available. So here we use the term available. Available means the whether critical section is available or not. Available means whether critical section is currently available or not. If available is false, okay, if available is false, if available is false, then not available will be true. Okay. If available is false, that means critical section is not available. Somebody else is in the critical section. If available is false, then not available will be true. Okay. So if not available is true, that means critical section is not available. In that case, it will be busy waiting. Okay. So this is called a spin lock. So now say this is process 1 which is checking whether it is available or not. Critical section is available or not. So it is not available. Say the critical section is getting used by some other process 2. Then as long as process 2 comes out of critical section, it should wait. So this is basically it is a busy wait or spin lock. Okay. So once if it is available, if available is true, if available is true, then not available will be false. In that case, this process P1, what it will do, it will make available as false. Why it is making available as false? Because P1 is now going to use the critical section. So P1 is entering to the critical section. So before entering it is making available as false, so that some other process, if P3 also want to use, it cannot enter, it will be waiting. Okay. Similarly, after accessing the critical section, what it will do, it will release the lock. So for releasing, it will just make available as true. So, so this is how, so this is how the acquire and release works, and this is how it can be used in a particular program. So before entering the critical section, the particular process first execute acquire lock. If the lock is available, it will get the lock. Otherwise, it will keep on waiting through a spin lock until it has not got. Spin lock is nothing but an loop. It is a it is a so this is called a spin lock. Okay, this is called a spin lock or busy waiting. Here it will be busy waiting until the lock is available. Once once it is available, that is once once the critical section is available, then it will enter the critical section, it will perform the activity, and then it will release the lock, and then it will execute the remainder section. Okay, so this is how basically Mutex lock works, and Mutex lock is a software based solution. Okay, the next concept we will be discussing is semaphore. So Semaphore uh, is a more robust solution than Mutex lock. Okay, Semaphore is a more robust solution to critical section problem than Mutex lock. This is also a software-based solution, and uh, and here semaphore is basically an integer variable. Semaphore is basically an integer variable. For every shared resource, we will have one semaphore. Okay, and this semaphore is generally represented by the term yes. Okay, so if there are more than one shared resource, then you may call it as S1 as one resource, S2 as another resource, like that. And the semaphore will typically take an integer value. Okay, what values it will take, all those we'll discuss. And and it uses two atomic operations. It performs two atomic or in division operations, which is called as wait and signal. Semaphores on semaphore, the semaphore can be accessed. Okay, the semaphore can be accessed through two indivisible or atomic operations, which are wait and signal. Wait is otherwise also called as P, and signal is otherwise also called as V. Okay. So wait is otherwise called as P, and signal is otherwise called as V. And this is how the typical wait uh, instruction appears. Okay, so wait and signal are atomic instructions, and this is how wait appears. So wait on the semaphore yes. So yes is connected to a shared resource. Okay, and yes holds an integer value. Okay, so in the wait, what we are checking whether yes is less than or equal to 0. If s is less than or equal to 0, then the particular process which called the wait will be in busy wait or spin lock. If s is not less than or equal to 0, then s will be decremented by 1. Okay. So this is how the wait instruction of semaphore is implemented. And the signal instruction, what it does is, it just increments s, nothing else. There is no waiting, nothing, no checking. It just increments s by 1. Okay. So let us discuss this with an example. But before that, I would like to say one thing. There are two types of semaphores we have. One is called as counting semaphore, which can, so as we already discussed, semaphore will take some integer value. The counting semaphore can take integer value of unrestricted domain. There is no restriction on that. It can take integer values from 1 to any number, or not only 1, 0 to any number, depending on the number of instances of a particular resource available. Okay. And the second type of semaphore is binary semaphore. Binary semaphore can take only values between 0 and 1. And the binary semaphore is similar to mutex lock. Okay. in your system, if the mutex lock feature is not available, then the mutex lock feature can be implemented using binary semaphore. So there are two types of semaphores we have. One is binary semaphore, the other one is counting semaphore. Binary semaphore will take integer value between 0 and 1, and counting semaphore can take integer value over an unrestricted domain. So basically semaphores are used for sharing uh, uh, resources. Basically semaphores are used to access shared resources without any conflict. Okay, fine. See, where we will use binary semaphore and where we will use counting semaphore, in the sense, assume that in your computer there is only one scanner. Okay, there is only one scanner, and more than one process want to use this scanner. Process P1 also want to use the scanner. Process P2 also want to use the scanner. Now this is also a synchronization problem. Both of them cannot be given, only one person should be given the access. So who should be given access? So that decision will be taken by an binary semaphore. That is, if the resource available is only one, then we use binary semaphore. Okay. So so binary semaphore will be initially initialized to 1 because you have one resource available. Okay. Now if P1 takes the resource, then this semaphore value will be decremented by 1. Okay, that is, initially it was 1, now after decrementing it will become 0. So that is, initially it was 1, while it was 1, P2 was given access to the particular semaphore connected device, that is a scanner. Now if P1 comes and check what is the semaphore value for this particular semaphore associated with the scanner device, it will found it is 0. 0 means somebody is using, so it will spin lock there, or it will do busy waiting. Okay, so basically we use binary semaphore if there is only one shared resources which has to be shared among more than one process. Okay, counting semaphore will be used when the number of instances of the resources available are more than one. Okay, say for example, in your computer, 5 printers are available. Okay, let us assume 5 printers are connected to your computer. So printer 1 to printer 5. Okay, so now it means what? 5 processes can be given access to the printer at the same time, because you have 5 different printers, not one printer. You have 5 copies of printer. So in this case, say there is a semaphore S which connects to all these printers. Okay, so all these printers were referred to the semaphore S. Now S will be initialized to 5. Now S will be initialized to 5. If process P1 comes and says that I want printer, okay, then it will check what is S. S is 5. Okay, so it means 5 copies of printers are available already. 5 instances of printers are available. So it will take one printer and it will decrement S by 1. So now S will become 4. Now S will become 4. Okay. Again, some other process P2 comes and check, I want to access a printer. Okay, it checks what is S value. S value is 4. So still 4 printers are available. So it will take one printer and it will make SS3. Again, P3 comes and checks, I want to access the printer. Printer is available or not. It will check the semaphore. What is semaphore? S is 3. So already 3 printers are available. So it will take one and it will make SS2. Again, P3 comes and checks whether the printer is available or not. So it checks the S value. Yes, it is available. S value is 2. So it takes the printer and it will make S as 1. Okay. So here this is actually P3 and this will be P4. Okay. So this is P3 and this is P4. Okay. So again, say P5, another process comes and check, I too want to access the printer, is the printer is available or not. yes, already there is one printer available, so it takes that printer and it will make S as 0. Okay. So now again P6 another process comes and check is the printer is available or not. No, it is not available, so it will wait. Okay. So it will wait through a busy waiting. Okay. So the point is basically semaphores are used on resources, okay, rather than memory location. And and if the number of resource available is only one, then we use a binary semaphore. If more number of the similar resources are available, then we use counting semaphore. Okay. So counting semaphore, what value it will take in the sense, how many copies of resource you have, how many instance of resource you have. So if the number of instances of the resource available is 5, so in this case if number of printers available is 5, then the initial value what it will be taking is 5. Binary semaphore will always take an initial value of 1 because there is only one copy of the resource we have. Okay, and if somebody got that resource, then it will become 0. Okay, so basically this is how the semaphore concept works. Okay, now let us try to understand this particular code. Okay, so let us discuss this for first for binary semaphore, how it works for binary semaphore. If it is a binary semaphore, what will be the value of s? The value of s will be 0. Sorry, s will be 1. S initial value. The s will be initialized with 1. Okay. So now say a particular process P1 wants this particular resource. It can be any resource. Okay, it may be a printer uh, or a joystick or any resource. So this particular process comes and check whether the resource is available or not. Yes, wait, it calls wait of yes, while yes less than or equal to 0. S is not less than or equal to 0. So it won't get into busy wait. Okay, there is no busy wait. So rather what it will do, it will decrement S. So now S is no more 1, S becomes 0. Okay, after decrementing S, this process will enter into critical section. That is, it will start using the resource. Now say another process P2 comes and P2 checks whether S is available or not. So it calls wait of S. Now it checks whether S is less than or equal to 0. Yes, S is less than 0. So P2 will be busy waiting. P2 will busy wait. How long it will busy wait? Until S becomes greater than 0. Okay. Say P1 uses this resource for some X amount of time. P1 is using this resource from X for X amount of time. Once the time X elapsed, P1 will call signal. P1 will call this particular function signal of S. Okay. So S is a shared variable which is shared by both P1 and P2. Okay, now what is S value? 0. So what it does? S plus plus. So it will increment S by 1. So once it incremented, it means that P1 has released the resource. P1 is no more using that resource. So now P2 is busy waiting, and it immediately once it is released, it will find that okay, S is not less than or equal to 0. So again, P2 will enter and P2 will make S as 0. Okay, P2 will make S as 0 and it will enter the critical section. Okay, now if some other process P3 comes, it has to wait. So this is how binary semaphore works. If it is a counting semaphore, how it will work? Assume assume S is initialized with 3 and say this particular semaphore S refers to a printer, and say in your computer there are 3 printers available. It means 3 processors can be given access to the printer at the same time because you have 3 instances of the printer. Okay, so S is initialized with 3. Say a process, say first the process, let us assume first the process P5 comes and it wants the printer. So it checks the semaphore, the respective semaphore, yes. And it checks whether S is less than or equal to 0. No, it's not less than or equal to 0. So it will decrement S by 1. So S will become 2. S will become 2 and it started using one printer. Okay, so it means the first printer it takes. It takes the first printer and it is using that first printer. Okay. Now another process P2, say P3 comes. P3 comes and it also want to access the printer. So it calls the wait and it checks whether s is less than or equal to 0. No, s is 2. So it takes that particular printer, second printer it takes, and it decrements s by 1. So s becomes 1. Okay, so second printer was given to p3. So now another process P1 comes, and it also checks whether the printer is available or not. So it calls wait of S, and while S less than or equal to 0, S is not less than or equal to 0. So it means there is a printer available. So it takes that particular printer. Okay, and it makes S to 0. It decrements S. So the third printer was given to P1. Okay. Now say another process P4 comes. P4 comes, it wants printer and it checks yes. It calls wait of yes, and it is atomic instruction. There it checks whether s is less than or equal to 0. Yes, it is equal to 0. So it has to busy wait. So P4 will be busy waiting here. It will keep on wait. How long it will wait? Until s becomes greater than 0. Okay, so say meanwhile P5 completes the job. P5, whatever it is using the printer, it is completed. So P5 will call signal of S. Signal of S will increment S. So from 0, once again it will become 1. Once again it will become 1. Okay, so P5 has released the resource. So what the moment it becomes 1, then P4 is keep on checking whether S is less than or equal to 0. No, now P5 has released, so S becomes 1. So it will get the printer and it will make it to and the first printer will be once again given to P4. Okay, so this is how it works. So meanwhile, if P3 and P1 also releases the printer, so already P4 made it 0. If P3 and P1 releases, then again it will become 1, and later it will become 2. Okay, so this is how counting semaphore works. So here basically we use two types of instructions. One is wait and signal. Okay, so wait is used to acquire the shared resource, and signal is used to release the shared resource. So, so this is the overall concept of semaphores. But other than this, semaphores can also be used for some other kind of usage. Also, semaphores can be used. Say, for example, consider this problem. It can be also used to solve various other synchronization problems. So what are the other synchronization problems? Let us discuss one example. Let us assume there are two processes P1 and P2. Okay, and it should be done in such a way that the instruction S1 should be executed before S2. Okay, but S1 is available in the process P1 and S2 is available in the process P2. Okay, S1 is an instruction available in the process P1 and S2 is an instruction available in the process P2. But while executing, this order should be maintained that S2 should never be executed before S1. Only after S1 gets executed, S2 should be executed. So this can be ensured using semaphores. So here is an example. So this is the part of P1, process P1, and this is the part of process P2. Two different processes. Okay. So in process P1, so this is the statement S1. So what we discussed, S1 should execute before P1. Okay. And S2 should execute, so S1 should execute before S2 and S2 should execute uh, after S1. Okay. So this order should be maintained. So what we are doing in process P1, after the instruction S1, you can keep an instruction like this, signal of synchronization. So synchronization is the name of the semaphore here. In the previous example, we have discussed the same name of the semaphores as yes, but semaphore name can be anything. Okay, so here the semaphore name is synchronization and it is initialized to 0. Its sync is initialized to 0. Okay, so what it will do in the sense, once S1 is completed, once S1 is completed, the P1 will send signal of sync. Okay, signal of sync. So say assume P1 is executing first. If P1 is executing first, then S1 will execute first. If S1 executes first, then it will say, then it will call signal of sync. You know the code for signal of sync. Signal of sync, it will just increment the sync. Okay. So what happens in the sense, sync will become 1. Sync will become 1. Okay. So now sync, which is initially 0, now has become 1. Say now after that P2 executes. Now P2 calls wait of sync. So in wait, we check whether synchronization is less than or equal to 0 or not. No, it's not less than or equal to 0. So S2 will be executed. So this order is maintained here. So no issues. But say the order is not maintained. Say assume P2 is executing first. Not P1 is executing. P2 is executing first. So there is a chance that S2 may be executed first, which should not happen. So in this case, what happens? Sync is initialized with 0. So, so before calling S2, P2 calls wait of sync. Wait of sync. So in the wait code, you know what it does. It checks whether sync is less than or equal to 0. If sync is less than or equal to 0, it will do busy wait. So as sync is equal to 0, here P2 will do busy wait or it will perform spin lock. That is, it won't continue beyond this statement. It will just spin lock here and it will be keep checking the sync value whether it is becoming 1 or not. So until then, it will be busy waiting. Okay. So so maybe after some times P1 will get access and P1 will execute S1 and then it will call signal. Okay, when it calls signal, the sync will become 1. Sync will be incremented to 1. The moment sync incremented to 1, this will come out of busy wait and then it will execute S2. Okay. So like this, synchronize a semaphore can also be used to solve other synchronization problems. Okay. So yeah. So so this is about semaphores. Okay. And so yeah, counting semaphore can be implemented as a binary semaphore. Yes, the binary semaphore is nothing but uh, the semaphore which takes values between 0 and 1. Okay, so if a counting semaphore takes only values between 0 and 1, then that can be called as a binary semaphore. Okay, so now the problem with the semaphore is, the problem or the disadvantage of the semaphore is the spin lock. So like how Mutex lock suffers from the spin lock problem, like that semaphores also suffer from the spin lock problem.